There are two versions of Mars that exist in the human mind. One is the planet of our modern age, the Mars we see in the pristine haunting images sent back by our robotic emissaries. It is a world of sublime, silent desolation, a planet-sized desert of ochre and rust scoured by winds of carbon dioxide and entombed in a cold so profound it can freeze the very air we breathe. For generations it was a cosmic tombstone, a monument to entropy, the cautionary tale of a world that lost its vital spark. It is a magnificent ruin, beautiful in its emptiness, a silent testament to the unforgiving nature of the cosmos. This is the Mars of fact, of data, of rock and dust and radiation. But another Mars, a far stranger and more vibrant world, has been slowly resolving into focus, beamed back to us, across hundreds of millions of kilometers of vacuum encoded in the digital language of our most ambitious robotic explorers. This other Mars is not a memory, but a ghost. A phantom world hiding in plain sight, its story written not in ink but in the language of geology, chemistry and planetary physics. Its scriptures are canyons deeper than any on Earth, its forgotten monuments are vast, smooth plains that defy explanation, and its whispers are strange minerals that can only form in the one substance that defines our own world, liquid water. And not just a little water, not a trickle, not a pond, not even a sea. The evidence painstakingly gathered and fiercely debated points to a conclusion so staggering, it threatens to rewrite our entire understanding of the solar system. It points to a global planet-altering, life-giving ocean. An ocean so vast, so deep, that it would have dwarfed any single body of water on Earth today. An ocean born from a cataclysm of unimaginable proportions. This is the story of that lost world. It is a detective story on a planetary scale, a journey back 4 billion years to witness the birth and death of a Martian water world. It is our story too, for in the search for water on Mars, we are ultimately searching for ourselves, for an answer to the most profound question we have ever dared to ask: are we alone? To find the ocean, we must first find the flood. We must travel to the scars. Look here at this web of colossal channels gouged into the Martian highlands. They are not like the meandering river valleys of Earth carved patiently over eons by the gentle persistence of flowing water. These are different. They are brutal. They are the geological signature of violence. These are the outflow channels, the gaping wounds from which the ancient Martian ocean was born. To stand at the edge of one like the Casas Valles would be to stare into an abyss wider than the Grand Canyon and thousands of kilometers long. For decades we struggled to comprehend the force necessary to carve such features. No earthly river, no matter how powerful, could have done this. The scale was simply wrong. It was a puzzle that hinted at a process so alien, so powerful, it defied our terrestrial experience. The answer when it came was terrifying. These were not carved by rivers. They were the result of mega floods, just deluges on a scale so immense they have no true parallel on our own planet. Imagine a dam breaking, not a dam of concrete and steel, but a dam of planetary crust miles thick. Beneath this crust, in the ancient Martian past, vast reservoirs of subsurface water, known as cryoaquifers, were held under immense pressure, superheated by the planet's internal warmth. For millennia, this subterranean ocean lay in wait, a sleeping giant trapped beneath the rock. Then something happened. Perhaps the immense weight of the Tharsis volcanic region, a bulge on the planet's side hosting the largest volcanoes in the solar system, fractured the crust. Or perhaps a massive asteroid impact shattered the seal. The trigger is still a matter of intense scientific debate, a clue we are still chasing. But the result is undeniable. The crust gave way, and the planet bled. It was a geological hemorrhage. Water pressurized for eons exploded onto the surface, not as a gentle spring, but as a roaring, unstoppable torrent. The flow rates were biblical apocalyptic. Scientists estimate that in a matter of mere weeks, or perhaps even days, these floods unleashed more than 100 million cubic meters of water per second. That is a flow rate 1,000 times greater than the Amazon River, the mightiest river on Earth. It is a volume of water that could fill the entire Mediterranean Sea in less than a month. This wasn't just water. It was a slurry of rock ice and mud, a planetary-scale landslide moving at hundreds of kilometers per hour. It was a force that didn't just erode the landscape, it annihilated it. It tore bedrock from its foundations, creating the streamlined islands you see today, teardrop-shaped hills of ancient rock, sculpted by a current more powerful than 1,000 hurricanes. It ripped open the chasms of the Valles Marineris and poured out onto the northern lowlands a cosmic fire hose aimed at the pole. Imagine the sound. A continuous deafening roar that would shake the very ground beneath your feet. A sound that would circle the thin Martian atmosphere for weeks. Imagine the sky choked with a mist of pulverized rock and vaporized water casting the young sun into a perpetual blood-red twilight. This was not a geological process in the way we understand it. It was a planetary convulsion. An event of such singular, catastrophic violence that it reshaped the face of an entire hemisphere in the blink of a geological eye. And this didn't just happen once. The evidence in the channels, the layers of sediment, the overlapping flow patterns, it all points to multiple successive flood events separated by thousands or millions of years. A repeating cycle of planetary trauma, each time releasing another titanic pulse of water from the planet's deep interior. And where did all this water go? It had to go somewhere. The laws of physics are relentless. On a planetary body, water, like everything else, seeks its lowest point. On Mars, that lowest point is a vast, smooth and eerily flat region that dominates the entire northern hemisphere of the planet, the Vastitas Borealis Basin. This basin, one of the flattest, smoothest places in the entire solar system, has long been a source of mystery. Its profound depression, sitting several kilometers below the planet's average elevation, makes it the natural collection point for any liquid. When we map the topography of Mars, the planet is clearly divided into two starkly different halves. The southern hemisphere is high, rugged, ancient, and heavily cratered. The northern hemisphere is low, smooth, and young. For years, scientists called this the Martian dichotomy, a fundamental mystery of the planet's formation. But the megafloods provided a stunning, elegant answer. The northern plains weren't just low, they were the bottom of a sea. The water from those cataclysmic floods, carrying billions of tons of sediment, poured into this immense basin, filling it up like a bathtub. The sediment settled, smoothing over the ancient craters, erasing the scars of the early solar system's bombardment, and creating the vast, featureless plains we see today. The water, the impossibly vast quantity of water, formed an ocean. An ocean we now call Oceanus Borealis. Its existence would fundamentally transform the planet. Mars would no longer have been just a red dot in the sky. It would have been a blue one, a true sibling to Earth, a world with a liquid heart. The scale of this ancient ocean is difficult to put into perspective. At its peak, it may have covered nearly a third of the Martian surface. Its waters would have filled the northern basin to a depth of over a mile in some places. The total volume of water in this single ocean could have been greater than all of Earth's oceans combined. Think about that. A planet half the size of our own, possessing more liquid water than we do. It's a concept that borders on science fiction, yet the evidence is etched into the very fabric of the planet. We believe we can even see its shorelines. Across the rugged highlands that form the basin's edge, planetary scientists have traced faint sinuous features, ancient beaches and terraces that appear to mark the boundary of this great lost sea. These potential coastlines, identified through high-resolution orbital imagery and laser altimetry, snake across the landscape for thousands of kilometers at a consistent elevation, just as a shoreline should. Imagine standing there on the shores of that Martian sea 4 billion years ago. The air would be thicker, then the pressure higher. The sky would not be the pale pink we see today, but a deeper blue, perhaps tinged with the red of suspended dust. The sun, younger and dimmer, would cast a soft ethereal light across the waves. The sound would be the most alien thing of all, not the silence of modern Mars, but the rhythmic crash of waves on a distant alien shore. Waves driven by winds sweeping across a fetch of water, hundreds, even thousands of kilometers wide. You would feel the damp air on your skin. You might see clouds, real water vapor clouds, scudding across the sky, a sight unseen on Mars for billions of years. There would be weather. There would be a water cycle. Evaporation from the ocean's surface would have formed clouds which would then travel south, precipitating as rain or snow over the highlands, feeding the very aquifers that would later burst forth in the great floods. It would have been a dynamic living system, a planet with a heartbeat. This ocean would have acted as a massive climate moderator, a planetary thermostat. The immense thermal mass of the water would have absorbed the sun's energy during the day and radiated it back at night, stabilizing the climate and preventing the wild temperature swings that plague Mars today. It would have created a global environment far more clement, far more stable, and far more friendly to the one thing that thrives in such conditions: life. The presence of a vast, long-lived body of liquid water changes everything. It is the single most important ingredient in the recipe for life as we know it. For hundreds of millions of years, this environment may have persisted. It was a window of opportunity, a period in Martian history when the planet was not a frozen desert but a temperate water world. A world with all the necessary ingredients: liquid water, a thicker atmosphere, a protective magnetic field generated by a still molten core, and a rich supply of complex organic molecules delivered by comets and asteroids. It was a perfect crucible. But how can we be sure a theory this grand requires extraordinary proof? The faint outlines of shorelines are tantalizing, but they are not enough. They have been debated for years, with some scientists suggesting they could be volcanic ridges or other geological artifacts. To prove the existence of an ocean, we have to go beyond topography. We need to find the chemical fingerprints it left behind. We must become cosmic archaeologists, digging through the layers of Martian time to find the irrefutable evidence that this sea was real. This is where our modern explorers come in. Orbiters like the Mars Reconnaissance, Orbiter, and rovers like Curiosity and Perseverance are not just geologists, they are time travelers. Their instruments allow them to peer into the past. Using ground-penetrating radar, they can map the layers of ice and sediment beneath the northern plains, searching for the telltale signs of an ancient seabed. Their spectrometers can analyze the chemical composition of the rocks, from orbit hunting for the specific types of minerals that form only in the presence of liquid water over long periods, and they have found them. Vast deposits of clay minerals called phyllosilicates, which form when rock is chemically altered by water over long periods. They have found sulfates, the Martian equivalent of bath rings minerals left behind as large bodies of water evaporated. These are not the signs of a fleeting flood, they are the chemical ghosts of a persistent, stable, and possibly salty sea. The distribution of these minerals creates a map, a chemical map that aligns with the proposed boundaries of the ancient ocean. The highlands are dominated by older volcanic rock, untouched by this process. But as you descend into the northern basin, into the bed of the proposed ocean, the chemistry of the planet changes. The rocks tell a different story, a wetter story. Perhaps the most compelling piece of evidence, however, comes not from the ground, but from the very air itself. The thin Martian atmosphere of today holds a crucial clue about its watery past. By analysing the ratio of different types of hydrogen atoms in the atmospheric water, vapor scientists have been able to calculate how much water Mars has lost to space over the eons. The results of this atmospheric science are stunning, and they provide an independent line of evidence that corroborates the geological story. The data suggests that Mars once possessed a volume of water so immense that it could have easily formed an ocean covering a significant portion of the planet to a depth of hundreds of meters. The water is gone, stripped away by the solar wind after the planet's magnetic field failed, but its isotopic signature remains a final fading whisper from a lost world of water. So we have the scars of the floods, the basin for the ocean, the faint lines of the coast, the chemical evidence of the seabed, and the atmospheric ghost of the lost water. Piece by piece, the puzzle is coming together. A new Mars is emerging from the red dust of the old, a world of breathtaking scale and drama, a world we are only just beginning to know. This lost blue planet poses the ultimate question. If Mars had an ocean larger than any on Earth, if it had a stable climate and all the necessary ingredients for hundreds of millions of years, what happened in those waters? In the warm, mineral-rich shallows of that ancient sea stirred by tides, under a young sun, did the slow, patient miracle of chemistry finally quicken into biology? Could the first life in our solar system have been Martian? The answer is waiting for us there, locked away in the ancient sediments of the seabed, the next chapter in this incredible story. And our search for it has already begun. The next step is to drill, to go beneath the surface and pull up a core sample of that ancient ocean floor to read its 4 billion-year-old story and to finally learn if we have always been alone in this small corner of the universe. To truly comprehend the ghost of a global Martian ocean, we must first travel back in time, back to an era when the very idea was not just improbable, but a scientific heresy. We must return to a vision of Mars born not from the digital eyes of orbiters, but from the hopeful gaze of human astronomers peering through lenses of polished glass across an unforgiving gulf of space. For decades, the story of water on Mars wasn't one of discovery, but of profound, captivating, and ultimately heartbreaking illusion. It began, as so many cosmic journeys do, with a simple point of light in the darkness, a wandering star that held a special fascination. Through the primitive telescopes of the 17th and 18th centuries, Mars was little more than a ruddy, shimmering disk. Yet even then, it offered up a tantalizing secret. Astronomers like Giovanni Cassini and William Herschel, with painstaking patience, noticed brilliant white patches at its poles. More astonishingly, these polar caps behaved in a way that felt deeply achingly familiar. They grew and shrank in a stately rhythm, a slow, seasonal pulse that mirrored the ebb and flow of ice on our own world. Here was the first clue, the first whisper of a planet that was not entirely alien. It was an observation that ignited a firestorm of speculation. Could this be water ice? Could Mars, like Earth, possess seasons, weather, and the one ingredient we believed was essential for life itself? The question hung in the air of observatories for 2 centuries, a profound and unanswered riddle. The problem was distance. The same immense void that protects us also blinds us, blurring detail and inviting the mind to fill in the gaps. And in the late 19th century, the human mind, armed with ever larger telescopes, would fill those gaps with breathtaking imagination. The story pivots on a single fateful word. In 1877, the Italian astronomer Giovanni Schiaparelli, charting the Martian surface with unprecedented detail, observed a network of faint linear features crisscrossing the planet's reddish plains. He called them canali, an Italian word that simply means channels, or grooves, a neutral geological term. But when his work was translated into English, canali became canals. The difference was seismic. A channel is a work of nature. A canal is a work of intelligence. That single, fateful mistranslation transformed Mars overnight. It was no longer just a planet with ice caps. It was a potential civilization. The idea was given rocket fuel by a wealthy, charismatic, and utterly convinced American amateur astronomer named Percival Lowell. Obsessed with the canals, he used his fortune to build a state-of-the-art observatory in the clear, thin air of Flagstaff, Arizona, for the express purpose of studying Mars. From his perch, Lowell did not just see canals, he saw a grand planetary-scale irrigation system. He envisioned an ancient, dying world, its inhabitants, brilliant engineers born of desperation, building a colossal network to channel water from the melting polar caps to their parched equatorial cities. Lowell's Mars was a tragic romance written across an entire world. He drew intricate maps naming the canals after mythical rivers on Earth, Ganges, Euphrates, Lethe. His books, filled with elegant prose and unshakable conviction, captured the public imagination like nothing before. For millions, this was no longer a matter of scientific debate, it was fact. Mars was inhabited. It was a civilization on the brink, a desert world whispering its last rites across the solar system. We, the people of Earth, were peering into the twilight of a sister world, witnessing a magnificent final struggle for survival. It was a narrative so powerful, so compelling, that it completely overshadowed the quiet, cautious work of professional astronomers. The search for water on Mars had become a search for Martians, but science at its core is a self-correcting enterprise. It is a slow, methodical grind, far less romantic than Lowell's grand visions, but infinitely more reliable. As telescopes improved, as new techniques like spectroscopy allowed astronomers to analyze the chemical composition of light from other worlds, the beautiful tapestry of Lowell's Mars began to unravel. Other astronomers looking through even more powerful instruments simply could not see his intricate network of canals. They saw smudges, dark patches, and crater rims, but no fine straight lines. The awful truth began to dawn. The canals were not on Mars. They were in the human eye. They were an optical illusion, a product of the brain's innate tendency to find patterns to connect disparate, blurry dots into a coherent line. The scientific community, having been burned by this spectacular flight of fancy, recoiled. The pendulum of opinion, which had swung so far towards a wet-living Mars, now swung back with brutal force. The canals were not just a mistake, they were a source of deep institutional embarrassment. And in correcting this error, science adopted a new hardened dogma. Mars was not a dying world, it was a dead one. The polar caps, once seen as vast reservoirs of water ice, were re-evaluated. Spectroscopic analysis suggested they were primarily composed of frozen carbon dioxide dry ice. The thin Martian atmosphere, it was calculated, was far too cold and rarefied to permit liquid water to exist on the surface for any length of time. It would either freeze instantly or boil away into nothingness. The dream of a water-rich Mars was over. The planet was recast in the scientific consensus as a cold, sterile and geologically inert globe. A crimson epitaph, cratered and unchanging, forever locked in a deep freeze. For nearly half a century, this was the Mars we knew. It was a world of profound disappointment, a cosmic mirror that had promised us neighbours and instead showed us only a void. The questions that had puzzled scientists for decades seemed to have been answered, and the answers were all relentlessly negative. This was the baseline, the established truth, as we finally prepared to leave our own world and touch another. The first robotic emissaries we sent were not explorers seeking an oasis. They were coroners dispatched to confirm a death certificate that had already been written. In July of 1965, humanity held its breath. NASA's Mariner 4 spacecraft, a marvel of engineering on a shoestring budget, was about to make the first ever close-up flyby of Mars. After a journey of 228 million miles, it would send back just 22 grainy black and white photographs. The entire scientific world was gathered waiting for these images to be painstakingly transmitted and assembled bit by agonizing bit. What would they show? Would there be any hint of Lowell's dying civilization? Any sign of Schiaparelli's channels? Any feature that might suggest a world more complex than a simple ball of rock? The images that slowly materialized were a profound shock. They were, in a word, lunar. The pictures revealed a surface that was utterly devastatingly cratered. It was a battered ancient landscape pummeled by cosmic impacts over billions of years. There were no canals, no cities, no signs of erosion by wind or water. The thinness of the atmosphere was confirmed, the pressure so low it was barely 1% of Earth's. Mariner 4 delivered a verdict written in craters and dust. Mars was not Earth's twin. It was the Moon's cousin. The data seemed to slam the door shut once and for all on the possibility of a wet dynamic Mars. The follow-up flyby missions, Mariner 6 and 7 in 1969, only reinforced this bleak picture, imaging more craters and the carbon dioxide South Polar Cap. The case appeared to be closed. But science is rarely about a single definitive moment. It is about accumulating evidence, and sometimes the most important clues are hidden in plain sight, dismissed as anomalies. The real revolution in our understanding of Mars would not come from a fleeting glimpse during a high-speed flyby. It required patience. It required a permanent vantage point. It required an orbiter. That orbiter was Mariner 9. Launched in 1971, its mission was not just to glance at Mars, but to stare at it, to map its entire surface over the course of a year. When it arrived, however, it was met with a planet completely obscured. A colossal planet-encircling dust storm was raging, the largest ever witnessed. For weeks, the spacecraft circled a featureless beige sphere, its high-resolution cameras seeing nothing but a sea of dust. Imagine the frustration in mission control. They had the most sophisticated mapping instrument ever sent to another world, and it was useless. All they could do was wait for the storm to subside, and as they waited, something incredible happened. The dust began to settle first at the highest elevations. 4 dark spots slowly emerged from the haze poking through the global cloud layer. Radar data confirmed they were colossal mountains, but as the air cleared further, their true nature was revealed. They were shield volcanoes, volcanic constructs so enormous they dwarfed anything on Earth. The largest Olympus Mons was 3 times the height of Mount Everest, and the size of the state of Arizona. This was the first sign that Mars was not the inert moon-like body we had believed. It had a violent geologically active past. The dust continued to settle, and as it did, another feature of biblical proportions slowly revealed itself. A gigantic gash in the planet's crust, a canyon system so long it would stretch from New York to Los Angeles if placed on Earth. Valles Marineris, the Mariner Valley. This was not a world that was geologically dead. It was a world that had been torn asunder by immense tectonic forces. The cratered wasteland of the Mariner 4 images was just one part of a much more complex and violent story. Mars had secrets. It had a history. The planet was slowly, tantalizingly unveiling its true face, and then mission controllers saw them. Hidden amongst the craters and volcanoes were other features. They were not the straight artificial lines of Percival Lowell's fever dreams. These were different. They were sinuous, winding and chaotic. They branched and meandered. Some started from patches of collapsed, jumbled terrain. Others formed vast outflow channels that dwarfed the Amazon. And most tellingly, they possessed features that any terrestrial geologist would recognize in an instant. Tributary networks' braided patterns and streamlined teardrop-shaped islands carved into the downstream side of ancient craters. This was not the work of wind. It was not the signature of a lava flow. This was the unmistakable, undeniable handiwork of flowing liquid, and on a scale that was difficult to comprehend. These were not mere riverbeds. They were the fossilized scars of cataclysmic floods of torrents of water that had once raged across the Martian surface with unimaginable fury. The images were breathtaking, but they were also deeply confusing. They posed a paradox that would dominate planetary science for the next 50 years. Here before our very eyes was irrefutable evidence of ancient rivers, deltas and floodplains. Yet this evidence was etched into the surface of a world where our understanding of physics said liquid water could not possibly exist. The old skepticism born from the ashes of Lowell's canals came roaring back. Scientists wary of repeating the mistakes of the past were incredibly cautious. The debate ignited. Could these features have been carved by something else? Perhaps they were the result of exotic flows of liquid carbon dioxide bursting forth from underground reservoirs. Or maybe they were sculpted by rivers of low-viscosity lava, which can sometimes mimic the patterns of water. Some even proposed that they were the result of fantastically powerful winds in a bygone era when the atmosphere was thicker. Every alternative was put on the table, because the primary option that vast quantities of liquid water once flowed freely under a warmer, thicker sky seemed impossible. It violated everything we thought we knew about the modern Martian environment. So the battle lines were drawn. On one side, there was the stark photographic evidence of features that looked for all the world like they had been carved by water. On the other side was the brutal physics of the planet's present-day cold, thin atmosphere. The two realities could not coexist. It was a contradiction at the heart of our understanding of Mars. We had found the ghost of a river, but the world it had flowed through seemed to be a physical impossibility. The planet was whispering a story of a completely different past, a past with a lost atmosphere, a lost warmth and a lost liquid. To prove it, we would need to move beyond simply taking pictures from orbit. We would need to go there. We would need to touch the ground, to taste the soil, and to search for the missing element itself, the water that had carved these enigmatic channels before vanishing, seemingly without a trace. Undefined. The tantalizing whispers from Viking had faded into a long, cold silence. For 2 decades, the question of Martian water remained trapped in a scientific purgatory, a frustrating landscape of ambiguous data and deeply entrenched beliefs. The red planet held its secrets close, its face a frozen mask of indifference. But a new age was dawning. Humanity was no longer content to simply listen for whispers from afar. We were preparing to launch an armada, a new generation of explorers designed not just to look, but to see, to touch, to taste the very chemistry of the Martian past. This was a coordinated assault on uncertainty, a flotilla of intelligence aimed at settling the debate once and for all. The era of passive observation was over. The era of forensic investigation was about to begin. It started from the heavens with a surveyor of unprecedented precision. In 1997, the Mars Global Surveyor arrived a machine whose purpose was to strip away the planet's mystique and render it in stark, quantifiable detail. Its most powerful instrument was not a camera in the traditional sense, but a laser altimeter named MOLA, a device that would meticulously map the planet's topography with vertical accuracy measured in mere meters. For years, it patiently fired billions of laser pulses, painting a portrait of Mars more detailed than any map of Earth's own hidden seafloors. And as this ghostly digital version of a world took shape on screens back home, ancient forgotten features began to emerge from the noise. Along the ragged dichotomy that separates the smooth northern lowlands from the cratered southern highlands, MOLA traced a line. It was a subtle feature, an almost imperceptible contour running for thousands of kilometers, yet it possessed a stunning telltale characteristic: it maintained a near-constant elevation. Geologists stared their minds racing through terrestrial analogues. They were looking at what appeared to be a paleo shoreline, the faint eroded bathtub ring left behind by a colossal, long-vanished body of liquid. This wasn't a channel carved by a flash flood. This was the potential ghost of a quiet standing sea, an ocean that would have filled the entire northern hemisphere. Yet it was still circumstantial, a compelling but ultimately spectral piece of evidence. The skeptics remained arguing for volcanic plains or tectonic coincidences. We needed something more tangible. We needed to find the water itself. That call was answered by the 2001 Mars Odyssey and orbiter, armed with a suite of instruments that could perceive the planet in wavelengths far beyond human sight. Its most revolutionary tool was the gamma-ray spectrometer, a device with an almost supernatural ability. It couldn't see water, but it could detect the presence of its fundamental building block, hydrogen. As Odyssey settled into its mapping orbit, it began to listen for the faint energetic signatures of elements in the top meter of the Martian soil. The initial data that streamed back was so dramatic, so utterly unambiguous, that the science team at first suspected a malfunction. Across the vast polar regions, the signal for hydrogen wasn't just present, it was screaming. The concentration was enormous, indicating that just beneath a thin veneer of red dust lay vast reservoirs of water ice, a buried cryosphere containing more frozen water than all of Earth's Great Lakes combined. This was a monumental discovery, a confirmation that Mars was not in fact bone dry. But it was ice locked away at the frigid poles. It answered one question while sharpening another: could this frozen water, this planetary permafrost, be the final resting place of a once warmer, wetter world? To find that out, we had to go down there. We needed geologists on the ground. And in 2004, we sent two of the very best. They were twins, the Mars exploration rovers Spirit and Opportunity. They were not static landers like their predecessors. They were mobile robotic laboratories, extensions of our own senses, designed to wander, to explore, and to read the pages of Mars's geological history written in its stones. Their landing sites were chosen with surgical precision, guided by the orbital revelations of MGS and Odyssey. Spirit was dispatched to Gusev Crater, a 166-kilometre-wide basin that appeared from orbit to be the floor of a dried-up ancient lake, fed by a long meandering river channel. Opportunity was targeted to the other side of the planet, to a smooth flat plain called Meridiani Planum. The reason for this choice was a peculiar mineral signature detected by Odyssey, a massive concentration of coarse-grained crystalline hematite, an iron oxide that on our world almost exclusively forms in the presence of liquid water. One site looked like a lake bed, the other smelled chemically of water. It was a brilliant two-pronged attack on the planet's greatest mystery. Spirit's story began with a profound sense of geological disappointment. After a heart-stopping airbag cushion landing, the rover's cameras gazed out not upon the layered sediments of a tranquil lake bed, but upon a bleak rubble-strewn plain of volcanic basalt. It seemed the ancient lake, if it ever existed, had been buried deep beneath eons of lava flows. The mission could have ended there, a frustrating near miss. But Spirit was a rover built for tenacity. For months it painstakingly traversed the rocky plains, its instruments finding little to challenge the dry volcanic narrative. The science team, driven by a stubborn hope, directed the rover on a long, arduous trek towards a distant set of hills they named the Columbia Hills. It was a gamble, a multi-kilometre journey fraught with risk for the solar-powered robot. As Spirit slowly, carefully climbed the slopes of Husband Hill, the geology began to change. The dark volcanic rock gave way to lighter layered outcrops. Here in these ancient eroded hills, the rover found rocks laced with sulfates and goethite minerals that whispered of a past interaction with water, then a stroke of immense good fortune born from mechanical failure. In 2007, Spirit's right front wheel seized up, forcing the rover to drive backward, dragging its dead wheel like a plough through the Martian soil. One day, as it churned the ground near a feature called Home Plate, the paralysed wheel scraped away the topsoil to reveal a patch of startlingly bright, almost pure white material. Analysis showed it was nearly pure silica. On Earth, this kind of deposit is found in hot springs or fumaroles environments, where hot mineral-rich water bubbles up from a volcanic underworld. Spirit had not found the placid lake it was looking for, but it had stumbled upon something just as profound, the ghost of a Martian hot spring, a hydrothermal system that would have been a perfect energy-rich environment for microbial life. It had found an oasis not of water, but of the undeniable memory of it. On the opposite side of the planet, Opportunity's story was one of immediate, breathtaking revelation. While Spirit's quest was a marathon of persistence, Opportunity's was a sprint of discovery from the very first day. The rover's bouncing airbag cocoon finally came to rest inside a small shallow depression, a tiny crater just 22 meters across that would be named Eagle Crater. When its cameras opened their eyes, the science team back on Earth fell into a stunned silence. They weren't looking at a vast, featureless plain. By sheer unadulterated luck, Opportunity had landed inside a geological treasure chest. Exposed in the crater wall right in front of the rover was an outcrop of layered bedrock. For the first time, we were seeing the planet's sedimentary history, its pages open for us to read. But even more astonishing was the ground itself. The reddish soil was littered with countless tiny grey spherules, each no bigger than a peppercorn. They were everywhere. The team nicknamed them blueberries, and they quickly became the mission's first great puzzle. What were they? Volcanic pellets, impact debris, or something else entirely? Opportunity extended its arm, placing its moose-bower spectrometer against these strange little spheres. The instrument, which identifies iron-bearing minerals, sent back a definitive answer. They were rich in hematite. This was the mother lode. The rover had landed directly on top of the very mineral signature that had drawn it to Meridiani Planum in the first place. On Earth, such hematite-rich spheres, known as concretions, form through the slow precipitation of minerals from water, percolating through porous water-saturated rock. They were in essence geological fossils, not of life, but of the watery environment that could have supported it. The blueberries were not scattered on the surface by some random process. They were weathering out of the bedrock itself. They were an intrinsic part of the story written in those rocks. It was a powerful, compelling piece of the puzzle, but the rocks themselves held an even deeper truth. Opportunity was equipped with a tool that would revolutionize planetary science, the Rock Abrasion Tool, or RAT. It was a high-speed grinding wheel, a miniature geological drill that could shave away the weathered outer rind of a rock to reveal its pristine interior. For the first time, we could look inside a Martian rock. The team chose a promising spot on the outcrop, a section they called El Capitan. The rat whirred to life, grinding for hours to create a small circular patch of fresh rock dust just 4.5 centimeters in diameter. What the rover's microscopic imager revealed inside was a geological Rosetta Stone. The rock was composed of fine, beautifully preserved layers, some no thicker than a fingernail. Within these layers were tiny vugs, or cavities shaped like slender crystals. The geologists on the team recognized them immediately. They were the moulds left behind after large tabular salt crystals had dissolved, a clear sign that this rock had once been saturated with salty brine that later evaporated. Then came the chemical analysis from the APXS spectrometer. The rock was packed with jarringly high concentrations of sulfur chlorine and bromine. These elements had combined to form jarosite, a potassium iron sulfate hydrate. On our planet, this is a mineral that only forms in highly acidic standing water. There was no other known way to create it. The evidence was becoming overwhelming. We had the hematite concretions formed in groundwater, the crystal moulds left by evaporating brine, and the jarosite chemistry screaming of an acidic pond or sea. But there was one final spectacular piece of proof, a signature visible to the naked eye. In the rock's fine layers, Opportunity's camera captured a delicate swooping pattern of intersecting lines known as crossbedding. It is a feature with an unmistakable origin, a fossilized ripple formed as underwater sand dunes are pushed along by a gentle, persistent current. You can see the same patterns today at the bottom of a stream or along a shallow coastline on Earth. This was not the mark of a flood. It was not the mark of ice. It was the signature of a persistent flowing body of liquid water, a current that shaped the sediments on a shallow Martian seabed billions of years ago. The verdict was in. The case was closed. Here at Meridiani Planum, Opportunity had delivered the irrefutable multi-layered proof that scientists had sought for generations. This place was once the floor of a salty acidic sea. The cumulative weight of the evidence from the orbital shorelines of MGS to the buried ice of Odyssey to Spirit's hydrothermal springs, and now Opportunity's ancient seabed was crushing. The old paradigm of a forever cold, forever dry Mars was shattered beyond repair. It was a moment of profound re-evaluation, a Copernican-scale shift in our understanding of a neighbouring world. The data transformed Mars in our collective imagination from a simple, static, cratered ball of rock into a complex, dynamic planet with a history as rich and potentially as life-giving as our own. The debate was no longer about if Mars had water. The new, far more profound questions were now, how much water was there? Where did it all go? And was it around long enough for life to take hold in its depths? The discovery of a small sea at Meridiani Planum was a triumph, but it was also a tantalizing clue to a much grander mystery. If these were the remains of a local sea, then what of the far greater ghost haunting the planet's northern hemisphere? What of that potential ocean, a body of water so vast it would dwarf all the lakes and seas Opportunity had just proven existed? Finding conclusive proof of ponds and streams was one thing. Confirming an ocean would change everything. The next chapter in our search would require us to lift our eyes from the ground beneath our rover's wheels and look to the vast, smooth horizons of the north, hunting for the definitive shoreline of a lost Martian world. And so, the case for a wet Mars remained a collection of brilliant yet disconnected fragments. We had seen the tantalizing hieroglyphs of ancient riverbeds carved into crater walls, the delicate fans of long-dead deltas and the curious teardrop shapes of islands, sculpted by some immense vanished flow. Each was a postcard from a forgotten epoch, a single haunting note from an unfinished symphony. But they were not enough. A river is not an ocean. A flood is not a world. To convince a skeptical scientific establishment to transform a compelling hypothesis into a foundational truth would require more than just scattered snapshots of localized water. It demanded a single unifying vision, a global tapestry woven from threads of evidence so strong and so intertwined that they could withstand any challenge. The search was on not for another channel or another gully, but for the grand planetary-scale scars that only a true world-spanning sea could leave behind. The moment was arriving when whispers would need to become a roar, when a mosaic of possibilities would finally have to coalesce into the irrefutable portrait of a blue world. The first thread in this new tapestry was not woven from a rock sample or a chemical signature, but from pure geometry. It came from an unprecedented new way of seeing Mars, an ability to strip away the veil of colour and shadow and perceive the planet's true and naked form. For decades, our maps of Mars were tragically incomplete, vast regions rendered as little more than their educated guesses. But as the Mars Global Surveyor settled into its meticulous polar orbit, its Mars Orbiter Laser Altimeter, or MOLAR, began its painstaking work. It was a mission of profound patience. Pulse by pulse, photon by photon, MOLAR fired billions of pinprick laser beams at the surface below, timing the return journey of each one to within a nanosecond. From this relentless cosmic survey, a new Mars began to emerge. It was a world rendered not in rusty reds and dusty ochres, but in the stark mathematical beauty of elevation. Lowlands sunk into cool blues and purples, while the great volcanic highlands blazed in fiery reds and whites. For the first time, we could trace the planet's gravitational contours with the precision of a master cartographer. We could finally see the lay of the land. And in that new map in the sweeping, desolate plains of the Northern Hemisphere, something extraordinary began to take shape. Planetary geologists staring at these new global datasets started tracing faint yet persistent lines. These were not canyons or ridges, but subtle, continuous contours of elevation that snaked their way across thousands of kilometers of terrain. They wound around the edges of the ancient craters lapped against the foothills of volcanic provinces and delineated the vast northern basin from the cratered southern highlands with an unnerving consistency. One of these features, which came to be known as the Arabia shoreline, was a ghost of a coastline stretching for an incredible 10,000 kilometers. A second higher and even older was christened the Deuteronoilus shoreline. Scientists realized they were not just looking at random geological formations. They were looking at the telltale signature of an equipotential surface, the precise gravitationally defined line that liquid held in a basin of any size must inevitably form. It was the unmistakable trace of a shoreline. You are seeing the bathtub ring of a vanished sea. Imagine standing on a Martian hill 4 billion years ago, watching the waves of this primordial ocean gently lap against the shore. The molar data was allowing us to reconstruct that exact waterline, a ghost etched into the planet's very bones. The elevation of the Arabia shoreline was found to be remarkably consistent, varying by only a few hundred meters over its immense length, a level of uniformity that could only be explained by the placid surface of a massive stable body of water. The evidence was topographic, written in the language of altitude and gravity, but its implication was profound. This wasn't a flood channel. This was the boundary of a calm, persistent sea that had endured long enough to carve its memory into the rock. And connecting to this immense basin were the outflow channels we'd seen before, but now they appeared in a new terrifying context. They were no longer just massive rivers. They were the planet's catastrophic spillways, the colossal wounds through which the waters of the southern highlands had hemorrhaged northward to fill this immense sea in floods so violent they defy terrestrial comparison. The scale of the Valles Marineras outflow alone suggests a torrent of water 1,000 times greater than the flow of the Amazon River, a continental-scale deluge that would have filled the Mediterranean Sea in a matter of weeks. The view from orbit was becoming clear. The northern third of Mars was not just a basin, it was an empty ocean bed, but a map, no matter how precise, is only a container. To prove there was an ocean, we had to find definitive proof of the water itself, a chemical fingerprint left behind in the soil. The grand topographic picture needed ground truth, a confirmation written not in lines on a map, but in the very minerals of Mars. This next crucial piece of evidence would come from an instrument of almost magical capability soaring high above the planet aboard the Mars Reconnaissance Orbiter. It was called CRISM, the Compact Reconnaissance Imaging Spectrometer for Mars. CRISM didn't just take pictures, it stared at the Martian surface and saw its chemical soul. By analysing the precise spectrum of sunlight reflected from the rocks below, it could identify specific minerals with astonishing accuracy. It was the equivalent of tasting the geology of an entire world from hundreds of kilometres away. And CRISM was programmed to hunt for a very specific class of minerals, a family of molecules that are on Earth the unambiguous children of water. They are called phyllosilicates. To you and me, they are the clays. Clays do not form in flash floods. They are not the product of ice or transient trickles of moisture. Their delicate layered crystalline structure is forged in the patient embrace of liquid water, over vast timescales, hundreds, thousands, even millions of years. They are the mineralogical signature of persistence. Finding clays on Mars would be like finding the waterlogged remnants of an ancient library. It would prove not only that water was present, but that it was present long enough to fundamentally alter the planet's geology, to slowly and patiently transform volcanic rock into soft, pliable clay. As CRISM began to build its own revolutionary map of Mars this time, coloured by chemistry instead of elevation, a stunning pattern emerged. The clays were not everywhere. They were concentrated almost exclusively in the most ancient heavily cratered terrains of the southern highlands areas, dating back more than 3.7 billion years. And crucially, they were found in thick-layered deposits, often within the deltas and river valleys that fed into the Great Northern Basin. The story was snapping into focus with breathtaking clarity. The oldest rocks from the planet's wettest era were saturated with these water-formed minerals. later volcanic flows that covered parts of this ancient terrain were conspicuously barren of clays, a stark geological dividing line between a wet past and a dry present. Rovers on the ground, like Opportunity and Curiosity, would later drive right up to these formations, drilling into rocks that were once the muddy bottom of a Martian lake or stream. They touched the evidence. They confirmed that what Grissom saw from orbit was real. These were not just rocks. They were ancient mudstones, their fine-grained layers telling silent stories of the gentle currents and placid pools. The two great lines of evidence were beginning to converge. The molar map had drawn the physical outline of the basin, the container for the ancient sea. Now the Grissom map was revealing the chemical residue of the water that had filled it, a clear trail of clay breadcrumbs, leading from the eroded highlands directly toward the ghostly shorelines of the Northern Ocean. The case was becoming powerfully compelling. We had the basin. We had the geological evidence of long-standing water within it. But one final question remained the most difficult and perhaps the most important of all: how much water was there? It was one thing to prove an ocean existed. It was another entirely to calculate its size, to measure its ghost. The answer, remarkably, was not hidden in the rock, but was written in the thin, cold air of the Martian atmosphere itself. To find it, we had to learn to read a chemical echo, an isotopic message that has been reverberating across the solar system for 4 billion years. The story begins with the water molecule itself, H2O. Most hydrogen atoms, the H and H2O, are made of a single proton and a single electron. But a tiny fraction of hydrogen atoms in the universe carry a passenger, an extra neutron, in their nucleus. This heavier version of hydrogen is called deuterium, or D. Water made with this isotope is often called heavy water. On Earth, for every 1 million hydrogen atoms in our oceans, about 156 of them are deuterium. This ratio, the D to H ratio, is a fundamental planetary fingerprint established when the world first formed. But on a planet with weak gravity like Mars, a planet that has been steadily losing its atmosphere to the solar wind for eons, something fascinating happens. Lighter particles escape more easily than heavier ones. Over billions of years, as ultraviolet radiation from the sun split water vapor high in the Martian atmosphere into its constituent parts, the lighter hydrogen atoms were preferentially stripped away, zipping off into space forever. The heavier deuterium atoms, however, found it much harder to escape Mars's gravitational pull. They were more likely to fall back and remain in the atmosphere. The consequence of this planetary scale filtering process is dramatic. As Mars lost its water, the remaining atmosphere became progressively and profoundly enriched in the heavier deuterium. The D to H ratio, therefore, is not a static number. It is a cosmic dipstick, a fossil record written in the very air. By measuring the D to H ratio in the Martian atmosphere, today we can calculate precisely how much lighter hydrogen, and therefore how much water, must have been lost over the planet's history to produce the ratio we now see. It is a piece of geochemical detective work of breathtaking elegance. For years, astronomers using powerful telescopes on Earth had measured this ratio and found it to be startlingly high, about 5 times that of Earth's oceans. Then, in 2013, the Curiosity rover quite literally tasted the air at Gale Crater. Its sophisticated SAM instrument analysed atmospheric samples and confirmed the number with stunning precision. The D to H ratio on Mars is in fact over 5 times higher than Earth's. Some ancient water trapped in Martian meteorites show a ratio 8 times higher. The implication was inescapable. For the atmosphere to be so heavily skewed towards deuterium today, Mars must have started with a colossal reservoir of normal water that has since been lost. This was the smoking gun. It was the final unassailable piece of the puzzle. The D to H ratio was a receipt for a lost ocean. Scientists could now perform a calculation that had for decades been pure fantasy. They could take today's elevated deuterium level and, working backward, mathematically reconstruct the original volume of Mars's primordial water. The number that emerged from these calculations was staggering, almost unbelievable. To reach the current atmospheric ratio, Mars must have once possessed at a minimum 20 million cubic kilometers of water. It was a volume of liquid so vast that it demanded a truly global ocean to contain it. The 3 great pillars of evidence now stood together in perfect, unshakable alignment. The topographical data from Mola showed us where. The water had to be a gargantuan basin in the northern hemisphere. the mineralogical data from Crescem showed us the chemical proof of its long-term presence, the clays that formed in its depths and along its shores. And finally, the atmospheric D to H ratio told us with mathematical certainty how much water there had been. It was the ultimate convergence, a triumphant synthesis of geology, chemistry, and atmospheric physics. The era of speculation was over. The era of modelling began. Feeding these three datasets, the shorelines, the mineral maps, the water volume, into powerful supercomputers, scientists could finally resurrect the ancient Martian ocean. And the vision it produced was one of the most sublime in the history of science. They called it Oceanus Borealis. A vast blue sea stretching across the entire northern hemisphere of the planet, covering nearly a third of its surface. In our solar system, only Earth and Mars would have possessed such a feature. This was not a collection of lakes or an inland sea. It was a true world ocean holding more water than Earth's Arctic Ocean, and reaching depths in the deepest parts of the basin of over a mile. We can now imagine it with scientific confidence. We can see the waves crashing against the shores of the Arabia Terra highlands. We can picture the icebergs carving from the polar cap and drifting south into its frigid waters. We can envision mist and clouds rising from its surface to create a thicker, warmer, and more dynamic atmosphere than the planet has known for billions of years. The conformation of this ocean did more than just solve the mystery of the planet's lost water. It fundamentally transformed our entire understanding of early Mars. It turned a cold, dead rock into a vibrant, living world, a world with all the necessary ingredients for life as we know it. The water was there, the chemistry was right, the energy from a young sun was present, and if all of that was true, it raised the most profound question of all. In the depths of that ancient alien ocean, was anyone or anything else there to see it? To stand on the shores of that ancient Martian ocean, nearly 4 billion years ago, would have been to witness a sight both familiar and profoundly alien. The water, perhaps stained red with iron-rich sediment, would have stretched to a horizon beneath a sky paler and pinker than our own. Waves driven by thin but persistent winds would have crashed against volcanic islands and the rugged shores of a primeval supercontinent. This was a world brimming with the single most essential ingredient for life as we know it. A world that possessed not just lakes or seas, but a true global ocean, a body of water so vast it could swallow every continent on Earth and still have room to spare. And yet look at Mars now. The silence is absolute. These shores of that ocean are now just indistinct geological markers in a world-spanning desert. The waves are frozen in time, their memory etched only in the contours of sand-blasted rock. The planet is a husk, a magnificent ruin entombed in crimson dust. This is the ultimate cosmic mystery, a planetary crime scene 140 million miles wide. We have found the ghost of a living world. Now we must ask the question that haunts every image our rovers send home. How does a planet drown its own oceans and then die of thirst? Where did all the water go? The answer we have learned is not a simple one. There was no single cataclysm, no one apocalyptic day on the Martian calendar. Instead, the death of the Martian ocean was a slow, agonizing execution, a planetary decline that unfolded over hundreds of millions of years. It was a story of theft on an unimaginable scale, a heist that began not on the surface but deep within the planet's very heart. Like Earth, the young Mars was born with a molten, churning iron core. This immense spinning engine of liquid metal generated a powerful magnetic field, an invisible shield of energy enveloping the entire planet. This magnetosphere was Mars's guardian, its silent protector against the most relentless foe in the solar system, the Sun itself. Our star is not a gentle, constant lamp. It is a raging nuclear furnace that continuously spews a torrent of charged particles into space. This is the solar wind, a phantom gale that travels at 1,000,000 miles per hour, a ceaseless storm of protons and electrons that scours everything in its path. Here on Earth, our magnetic field deflects this onslaught, channeling the deadly radiation towards the poles, where it ignites the atmosphere in the ethereal dance of the auroras. Our shield holds, and our world remains safe beneath its protection. But on Mars, something went terribly wrong. For reasons we are still struggling to fully comprehend, the Martian dynamo faltered. Being smaller than Earth, its internal heat dissipated more quickly. The molten core, once a raging furnace, began to cool and solidify. The great engine stuttered, sputtered, and sometime around 4 billion years ago it died, and with its death the planet's global magnetic shield vanished. Suddenly Mars was naked and exposed. The solar wind, which had for eons been held at bay, could now strike the planet with its full unrelenting force. The grand theft had begun. The target was the Martian atmosphere. While thicker than it is today, this early atmosphere was still the only thing keeping the ocean in a liquid state. It was the planetary blanket providing the necessary air pressure to prevent the water from simply boiling away into space. Without the magnetic shield, the solar wind began to act like a celestial sandblaster. Particle by particle, molecule by molecule, it began to strip the atmosphere away. High-energy solar radiation crashed into the upper atmosphere, imparting enough energy to individual atoms of gas to accelerate them past their escape velocity. It was a slow, insidious process, an erosion of the sky itself. Oxygen, nitrogen, argon. The very gases that held the ocean in place were being siphoned off into the void. NASA's MAVEN spacecraft orbiting Mars since 2014 has acted as our forensic detective. It has tasted the tenuous remnants of the Martian air, measured the escaping ions, and confirmed this process of solar stripping is still happening today, albeit at a much slower rate. By analysing the telltale isotopic ratios in the remaining atmosphere, scientists have been able to rewind the clock to calculate the sheer volume of air that has been lost. The data paints a grim picture of a world being steadily dismantled by its own star. The loss was not uniform. It was likely punctuated by violent solar flares and coronal mass ejections, billion-ton clouds of magnetised plasma from the Sun that would have struck Mars like atmospheric tsunamis, carrying away huge swathes of the sky in a single devastating blow. As the atmosphere thinned, the pressure at the surface began to plummet. The blanket was unravelling thread by thread. This slow solar stripping may have been the primary culprit, but it wasn't the only one. The early solar system was a far more violent place, a cosmic shooting gallery of leftover planetary debris. Mars was relentlessly battered by colossal asteroid and comet impacts events that possessed an energy that dwarfs our entire nuclear arsenal. An impact from a large enough body would do more than just carve out a crater. The resulting explosion would be so powerful, it could literally blast a column of atmosphere clean out of the planet's gravitational well, ejecting it permanently into interplanetary space. Each major impact was another wound, another catastrophic breach in the planet's dwindling atmospheric reserves. Between the steady erosion from the Sun and these violent explosive losses, the fate of the Martian atmosphere was sealed. With its protective blanket gone, the surface pressure dropped to a critical point. On the shores of the Great Northern Ocean, the water would have begun to boil, not from heat, but from the lack of pressure holding it together. The ocean, that vast world-defining feature, began to literally evaporate into a sky that could no longer contain it. The planet's climate spiraled into a catastrophic, irreversible collapse. The greenhouse effect, which had kept the planet warm enough for liquid water, failed. Temperatures plunged across the globe. Mars was transforming, shedding its blue skin for the frozen red one we see today. This brings us to the second part of our mystery. We understand how the conditions for liquid water were destroyed, but what became of the water itself? An ocean larger than our Atlantic did not simply vanish without a trace. A significant portion exposed to the harsh glare of an unfiltered sun was lost to space forever. Ultraviolet radiation, no longer blocked by a thick ozone layer, sliced through the water vapour in the upper atmosphere. This process, known as photodissociation, split the H2O molecules into their constituent parts, hydrogen and oxygen. The oxygen, being heavier, may have fallen back to the surface, reacting with the iron-rich rock to create the ferric oxides that give Mars its distinctive red colour. The planet literally rusted. But the hydrogen, the lightest element in the universe, was a cosmic fugitive. It effortlessly escaped Mars's weakening gravitational grip, bleeding out into the void, lost to the solar system for all time. Every molecule of hydrogen lost was a molecule of water that could never be recovered. Still, even this process cannot account for the entire volume of that ancient sea. The majority of the Martian ocean, we now believe, never left the planet at all. It is still there. It is simply hidden. As the planet froze, vast quantities of water were locked away as ice. We see the most obvious evidence of this at the poles. The polar ice caps of Mars are monumental structures, layered deposits of water ice and frozen carbon dioxide that rise 2 miles above the surrounding plains. They are the visible tombs of the ancient climate, containing a climatic record stretching back millions of years in their alternating layers of ice and dust. But even these colossal glaciers represent only a fraction of the original ocean. The real reservoir, the great planetary secret, lies buried beneath our feet. Mars, we now suspect, possesses a global cryosphere, a layer of permafrost and subterranean ice that extends for miles below the surface. The ocean did not so much disappear as it retreated underground. Ground-penetrating radar from orbiters like the Mars Reconnaissance Orbiter has given us tantalizing glimpses of this hidden world, detecting massive sheets of pure water ice, some as large as the state of California, buried just beneath a thin veneer of red dust. In the mid-latitudes, we see strange geological features, lobat debris aprons, lineated valley fill, that look for all the world like immense glaciers covered in rock and soil, slowly flowing over millions of years. It seems the ocean seeped downwards, freezing into a solid planet-spanning aquifer of ice, a frozen ghost of the world that was. This vast subterranean repository could hold enough water to cover the entire planet to a depth of over 100 feet. But there is one final extraordinary piece to this puzzle, a fate for the water that is perhaps the most profound of all. It suggests the ocean wasn't just lost or frozen, it was absorbed. It became part of the planet's very bones. When water interacts with rock, it doesn't just sit on the surface. It drives chemical reactions, a process known as aqueous alteration. Minerals that were originally formed in dry volcanic conditions are transformed into new hydrated minerals, clays, sulfates and carbonates, that incorporate water molecules directly into their crystal structure. The water ceases to be a liquid and becomes a fundamental component of the rock itself. Our rovers, from Opportunity to Curiosity to Perseverance, have confirmed this on a planetary scale. Everywhere they look, they find these altered rocks, the chemical fingerprints of a time when vast quantities of water soaked the Martian crust. This leads to a startling hypothesis: the Martian crust acted like a giant geological sponge. Over hundreds of millions of years of interaction with the ocean, it relentlessly wickered the water out of the surface environment and sequestered it into the lithosphere. The planet literally drank its own ocean, locking it away in a mineral prison from which it could not escape. According to some models, this process alone could account for a volume of water equivalent to half of the original ocean. It didn't escape to space. It didn't just freeze underground. It was petrified, becoming an inseparable part of the very ground we're now exploring. The Red Planet is, in a very real sense, a world built from the remains of its own lost sea. So we finally have the elements of a complete answer: a dying core, a collapsing magnetic shield, and a relentless solar wind that tore the sky apart. A climate that spiraled into a deep freeze, locking one part of the ocean into subterranean glaciers. A thirsty crust that absorbed another vast portion, turning it to stone. And a final fraction dissociated by sunlight that bled away into the eternal night of space. This multi-pronged assault transformed a vibrant, water-rich world into the desolate frozen desert we see today. This timeline of catastrophe has profound implications for the one question that drives our entire exploration of Mars: the question of life. It tells us that there was a window of opportunity. For a brief period, in cosmic terms, perhaps a few 100 million years, Mars had it all: a thick atmosphere, stable temperatures, and vast flowing bodies of liquid water. All the known prerequisites for life were present. But that window did not stay open for long. The story of Mars's lost ocean is the story of that window slamming shut with brutal planetary finality. The true tragedy of Mars may not be that it was always barren, but that it was alive with possibility for a fleeting moment, only to have that promise extinguished. We are therefore exploring not just a different planet, but a different time. We are sifting through the fossilized remains of a more hopeful era. The water is gone from the surface, the atmosphere is a ghost of its former self. The vibrant blue marble has become a silent red tomb. But what if something from that brief glorious spring managed to endure? What if the retreat of the water was not an extinction event, but a migration? Could evidence of that ancient life, or perhaps even life itself, have followed the water downwards, taking refuge from the harsh surface in the deep, dark places of the planet? The mystery of where the water went is largely solved. But in solving it, we have unearthed a much deeper, more tantalizing question. What if anything went with it? The search for the ocean's ghost has now become a hunt for life's last, most tenacious hiding places. And so, the trail of breadcrumbs scattered across 4 billion years of planetary history had led us here. The ghost of an ocean vast and deep was no longer a matter of speculation, but a geological certainty its shorelines etched into the very bones of Mars. But this profound discovery only deepened the central haunting mystery. If a body of water dwarfing all of Earth's oceans once filled the northern plains, where did it go? An entire planet's worth of water does not simply vanish. It must be somewhere. The next chapter in this grand detective story would demand a new generation of explorers, not paleontologists of rock, but hydrologists of an alien world, armed with instruments that could finally pierce the veil of red dust and peer into the planet's heart. The hunt was no longer for the memory of water, but for the water itself. Our first clues came not from the ground, but from orbit, with instruments of almost impossible sensitivity. The European Space Agency's Mars Express and NASA's Mars Reconnaissance Orbiter became our eyes in the sky, equipped with powerful ground-penetrating radar systems. Think of it not as a camera, but as a kind of cosmic sonar sending radio waves deep into the Martian crust. These waves travel downward, bouncing off different layers of material rock dust and, if it was there, ice. By timing the faint echoes that returned to the spacecraft, scientists could build a three-dimensional map of the world beneath the world, a geological cross-section of the planet's secrets. For years, these orbital surveyors patiently scanned the surface painting, a picture of the Martian subsurface mile by painstaking mile. They confirmed what we had long suspected: the polar caps were not merely thin veneers of frost. They were colossal structures, titans of frozen water and dust layered like pages in a history book, some extending more than 2 miles deep. Here was a significant portion of the missing water locked away in a planetary deep freeze, a visible remnant of that wetter, warmer past. But then in 2018, the MARSIS instrument on Mars Express detected something that sent shockwaves through the scientific community. Beneath the southern polar ice cap, nearly a mile down its radar pulses, returned an echo of extraordinary brightness. It was a signal so strong yet reflective that it defied explanation as mere rock, or even solid ice. After years of meticulous analysis ruling out every other possibility, the conclusion was as inescapable as it was electrifying. They had found a lake, a pocket of liquid water stretching nearly 12 miles across, hidden in the eternal freezing darkness beneath a mountain of ice. This wasn't the ghost of water, this was the genuine article kept from freezing by the immense pressure of the ice above, and most critically by an extremely high concentration of salts. These perchlorate salts, known to be abundant on Mars, act as a powerful antifreeze, lowering the freezing point of water, dramatically allowing it to remain liquid at temperatures far below what we experience on Earth. Suddenly, the search for Martian water was transformed. It wasn't just a quest for ancient desiccated riverbeds or frozen poles. It was now a hunt for hidden subterranean habitats, dark, cold, briny ecosystems that bore a startling resemblance to the subglacial lakes of Antarctica, like Lake Vostok, where microbial life on Earth has been found to thrive, cut off from the outside world for millennia. Mars, the planet we thought had died, was showing a faint hidden pulse. While our orbital sentinels listened for echoes from the deep, our robotic emissaries on the surface were engaged in a more intimate investigation. They were our hands, our eyes, and our chemical laboratories on the ground, tasked with sifting through the very soil that once lay at the bottom of the Martian lakes and rivers. In Gale Crater, a 96-mile-wide basin, with a towering mountain of layered sediment at its centre, the Curiosity rover had been diligently at work since 2012. Its mission, in essence, was to follow the water. And it succeeded beyond anyone's wildest dreams. Early in its journey, it drove over rounded pebble stones so smoothly worn they could only have been tumbled for miles in the current of a fast-flowing, persistent stream. This wasn't a flash flood. This was a riverbed proof of flowing water that was more than just a fleeting event. As Curiosity ascended the foothills of Mount Sharp, it drilled into mudstone's fine-grained sedimentary rocks that form only at the bottom of a calm-standing body of water like a lake. And within these ancient lakebed deposits, Curiosity's sophisticated internal laboratory, the SAM instrument, made a landmark discovery. It found complex organic molecules. Now we must be absolutely clear. Organic molecules are not life. They are, however, the fundamental building blocks of life as we know it, the carbon-based chemistry from which biology arises. Finding them preserved in 3-billion-year-old mudstone was a monumental step. It told us that the ancient Lake and Gale crater contained not only water, but also the raw ingredients necessary for life to begin. It was like finding a fully stocked kitchen in an abandoned house. It doesn't prove a chef was ever there, but it shows that all the essentials for a magnificent meal were present. The Martian environment for a very long time was not just habitable in theory. It possessed the chemical toolkit for a potential genesis. The question of whether that spark ever ignited hung heavy in the thin, cold air. To answer that, we would need a new kind of explorer, one designed not just to find habitable environments, but to actively hunt for the fossilized fingerprints of life itself biosignatures. That explorer is Perseverance, landing in 2021 in Jezero Crater, a location chosen with surgical precision from years of orbital data. It represents the sharpest point of our scientific spear. Jezero wasn't just any crater. It was the site of a spectacular ancient river delta. Billions of years ago, a powerful river breached the crater wall, slowing as it entered a vast lake and depositing enormous quantities of sediment in a classic fan-shaped delta. On Earth, river deltas are biological hotspots incredibly effective at preserving organic materials and signs of life in their fine-grained clays. If life ever existed on Mars, a place like Jezero is one of the very best places we could possibly look for its remains. Perseverance is a marvel of engineering, a rolling astrobiology lab. Its robotic arm is equipped with a suite of instruments that would be the envy of any university geology department. An instrument named PXL fires a hair-thin X-ray beam to map the elemental composition of rocks, revealing their history with microscopic detail. But its true purpose is embodied by Sherlock and Watson, a pair of instruments designed for the ultimate treasure hunt. Using an ultraviolet laser, Sherlock scans the rock, causing certain minerals and organic compounds to fluoresce to glow in the dark. It is a technique for finding needles in a planetary-scale haystack, highlighting patches of concentrated organics that warrant a closer look. This is the first step in identifying a potential biosignature. We aren't necessarily looking for a fossilized Martian trilobite. Biosignatures can be much more subtle. They might be microscopic textures in the rock that could only have been formed by colonies of microbes creating what we call stromatolites. They could be specific types of lipid molecules known to be produced by living organisms, a kind of chemical fossil. Or they could be an unusual concentration of a particular element, a chemical imbalance in the rock, that suggests the mediating influence of biology. Perseverance's task is to find these tantalizing targets, to document them with unprecedented precision, and most importantly, to collect and cache the most promising samples. In a series of pristine sealed tubes, it is gathering the geological soul of Mars, leaving them on the surface for a future mission, a mission that will be the first in history to launch from another planet and bring those precious samples back to Earth. Only then in our most advanced laboratories will we be able to make the final determination to answer the question that has driven us for centuries. Yet even as our rovers scour the surface, Mars continues to surprise us, revealing that its water story is not entirely relegated to the past or the deep subsurface. Our orbiters have noticed strange dark streaks appearing on certain sun-facing crater walls and slopes during the warmest months of the year. These features, called recurring slope lineae or RSLs, lengthen down the slopes in the Martian summer and then fade away as winter approaches. They look for all the world like damp patches, like seeping water darkening the sand. Spectrographic analysis from orbit detected the chemical signature of hydrated salts within these streaks, the very same kind of brines we believe are keeping the subglacial lakes liquid. This is the most compelling evidence we have for liquid water existing, however, ephemerally on the surface of Mars today. These seeps are not vast rivers, but perhaps tiny, intensely salty trickles that emerge from underground aquifers, when the temperature rises just enough. They are tantalizing yet frustratingly difficult to study up close, as the steep unstable slopes where they appear are too dangerous for our rovers to navigate. Are these seeps sterile chemical phenomena, or could they be tiny seasonal oases for some kind of hardy salt-loving Martian microbes? The planet continues to guard its deepest secrets. And finally, to truly understand where the water went, we had to look up into the thin residual atmosphere that remains. The MAVEN spacecraft arriving at Mars in 2014 was designed with one primary purpose: to be a planetary medical examiner to perform an autopsy on a dead atmosphere. For billions of years, Mars has been a world without a protective global magnetic field. Unlike Earth, whose magnetic dynamo shields us, Mars has been left naked and exposed to the harsh solar wind, a constant stream of charged particles flowing from the sun. MAVEN's data painted a grim, dramatic picture of atmospheric theft on a planetary scale. It measured solar wind particles slamming into the upper atmosphere, stripping away lighter gas molecules and flinging them out into space, a process that continues to this day. Over eons, this relentless solar scouring has been a celestial blowtorch eroding the Martian air. The crucial insight came when MAVEN measured the ratio of heavy to light hydrogen in the atmosphere. The lighter hydrogen isotopes are stripped away more easily, leaving the heavier form deuterium behind. By measuring the current highly enriched ratio of deuterium, scientists could calculate precisely how much water Mars must have lost to space over its lifetime. The numbers were staggering. The volume of water that escaped into the void was more than enough to have filled that colossal northern ocean with depths reaching over a mile. Here then was the answer to our question. Some of the water is frozen at the poles and locked underground. But the vast majority of that ancient ocean was lost molecule by molecule in a slow, inexorable atmospheric exodus that spanned geologic time. This atmospheric investigation, however, uncovered one more final, electrifying puzzle. Our rovers on the surface, particularly Curiosity, have been sniffing the air, and they have smelled methane. On Earth, over 90% of atmospheric methane is produced by living organisms, from microbes to cows. While it can also be produced by geological processes, its presence on Mars is deeply intriguing. It's not a constant, steady presence. Instead, it appears in mysterious puffs, seasonal spikes, where the local concentration of methane suddenly increases tenfold, only to dissipate again. We have detected it from orbit, and we have confirmed it from the ground. Something on Mars is periodically releasing plumes of methane gas. We do not know if the source is a geological reaction between water and rock deep underground, or if it is the faint collective exhalation of microbial life, perhaps dormant for most of the year, that becomes active when conditions are just right. It is one of the most provocative and debated mysteries in modern planetary science. Is Mars breathing? Are we detecting the faint metabolic pulse of a biosphere hidden just beyond our reach? A ghost in the machine. And so, all the threads of our investigation begin to converge, weaving a new and far more complex portrait of the red planet. We have found the buried ice a vast reservoir of its former glory. We have detected the briny subglacial lakes offering the tantalizing prospect of modern habitats. We have discovered the organic building blocks of life in ancient mud, confirming the planet's past potential. We have witnessed the ephemeral seeps of salty water, a sign of ongoing hydrological activity. We have measured the atmospheric ghost of the lost ocean and sniffed the inexplicable scent of methane on the wind. Each discovery is a crucial piece of the puzzle, pointing toward a single profound possibility. The evidence no longer supports the image of Mars as a planet that was merely habitable once, and is now sterile and dead. Instead, it suggests a world in transition, a planet whose life-giving water did not vanish but retreated into the crust, into the ice, into hidden brines. It raises the ultimate question. If life did begin in that great northern ocean, is it possible it did not die out? Could it have followed the water, adapting and evolving, migrating downward into a subterranean refuge, a biosphere hidden from the harsh radiation and bitter cold of the surface? We may be standing on the precipice of one of the most monumental discoveries in all of human history, the confirmation of a second genesis, a separate independent origin of life on a neighbouring world. The hunt for water has led us to the threshold of the hunt for life itself, and the next steps we take may finally answer the question of whether we are in fact alone. and so the final mirage solidifies into truth. The last ghost flickers and becomes real. For generations we saw Mars through a glass, darkly projecting our own hopes and fears onto its ochre plains. We imagined canals, then we accepted desolation. We found a planet of extremes, a world of magnificent silent geology. But beneath the silence, a story of unimaginable scale was waiting. A story that required us to unlearn what we thought we knew, to connect disparate clues, scattered across a world, and to finally accept a staggering revelation. The quiet, frozen planet we see today was once a vibrant, dynamic, and profoundly wet world, cradling an ocean vaster than any single sea on Earth. This is not speculation. This is not a dream. It is the breathtaking culmination of a planetary detective story, centuries in the making, a testament to our relentless curiosity. The evidence once a trickle has become a flood, washing away our old ideas and leaving us standing on the shores of a completely new Mars. We now see that every canyon, every sinuous channel, every mineral deposit is a form of planetary scar tissue, a faded memory of a time when water was the dominant architect of the Martian landscape. The journey to this understanding was an epic in itself, a multi-generational quest that began not with rovers, but with human eyes pressed to brass telescopes. It began with the tantalizing, ultimately flawed vision of Percival Lowell, whose intricate maps of Martian canals ignited a global fascination. His canals were an illusion, a trick of light and longing, but they planted a seed. They dared us to imagine a Mars that was not static, a world with a history, a world that could be like our own. When the first grainy images from Mariner 4 swept past the planet in 1965, they seemed to shatter that dream forever, revealing a cratered moon-like surface, cold and apparently lifeless. The public imagination, once fired with visions of alien engineers, grew cold. Mars, it seemed, was a cosmic disappointment, but science is a patient pursuit and the planet was not done revealing its secrets. The true revolution began with Mariner 9, the first spacecraft to orbit another world. As a global dust storm cleared, it unveiled something that Lowell could never have seen but would have understood instantly: immense branching canyons and dried riverbeds, carved not by intelligent hands, but by the raw elemental power of flowing water. Valles Marineris, a gash in the planet's crust so vast it would dwarf the Grand Canyon, was not a crack, but a feature profoundly shaped by water. The dream of a living Mars was reborn this time not as fantasy, but as a thrilling scientific hypothesis. The Viking landers of the 1970s touched down on this enigmatic world, scooping its red soil in search of life's chemical signatures. Their experiments were brilliant, their results maddeningly ambiguous. They found a chemically reactive soil, but no definitive proof of biology. They gave us our first panoramic views from the surface, showing us a landscape of rocks and ruddy dust under a pale pink sky, a place of profound beauty, but also profound loneliness. For a time, the pendulum swung back. Mars was ancient, yes. It had water in its past, yes. But it was now seen as a world whose promise had expired billions of years ago. It would take a new generation of robotic explorers, a fleet of orbiters, landers and rovers to piece together the full, staggering truth. They were our proxies, our eyes, our hands, our rolling chemical laboratories on another world. The Mars Global Surveyor mapped the planet with unprecedented precision, tracing the faint outlines of what looked suspiciously like ancient shorelines, vast continent-spanning contours etched at a consistent elevation. From orbit, the Mars Reconnaissance Orbiter with its piercing vision identified hydrated minerals, clays, sulfates, and silica, the telltale chemical fingerprints left behind by water interacting with rock over immense timescales. These weren't just in a few isolated craters. They were spread across enormous regions, painting a picture of a long-standing, globally influential aqueous environment. Down on the surface, the story became even more tangible. The little rovers that could spirit an opportunity became our field geologists. At Meridiani Planum, Opportunity hit the scientific jackpot, discovering small hematite-rich spheres the science team nicknamed blueberries. On Earth, such concretions form exclusively in the presence of abundant groundwater. The rocks here were layered with sulfate salts that form when bodies of salty water evaporate. Opportunity was driving across the floor of an ancient ephemeral sea. Then came curiosity, a behemoth of a rover sent to Gale Crater, a place chosen specifically because it looked like it once held a lake. And that's precisely what it found. It drilled into mudstones rocks formed from fine silt settling at the bottom of a calm body of water over millions of years. This wasn't a flash flood. This was a persistent, stable, life-friendly lake with a chemical composition so benign you could have safely drunk the water. Curiosity's data allowed us to taste, in a chemical sense, the fresh water of ancient Mars. Its successor Perseverance was sent to an even more tantalizing target, Jezero Crater, the site of a perfectly preserved river delta. A delta is a geological billboard announcing in giant letters that a river once flowed into a standing body of water, a lake or a sea or an ocean. Perseverance is now caching samples from this delta, samples that we'll one day bring back to Earth, samples that may hold within their fine-grained layers the fossilized remnants of Martian biology. Each mission was a crucial thread, but woven together they created a rich and undeniable tapestry. The paleo shorelines seen from orbit, the waterlogged minerals, the lake bed mudstones, the stunning deltas, they all pointed in one direction. They pointed north. They pointed to the vast low-lying basin of the northern hemisphere, the smoothest, flattest region on the entire planet. They pointed to the former site of Oceanus Borealis, the great northern ocean of Mars. Understanding this changes everything. It reframes our entire search for life beyond Earth. For decades, that search has been guided by a simple mantra: follow the water. Now we see that on early Mars you wouldn't have needed to follow it. You would have been submerged in it. An ocean provides not just a simple puddle of water, but a vast, stable environment with a dazzling array of potential habitats. Think of the sheer diversity of life on Earth's ocean floors. You have sunlit coastal regions perfect for photosynthetic organisms. You have the crushing darkness of the abyssal plains where life thrives on chemical energy. And you have the searing heat of hydrothermal vents, those volcanic fissures on the seabed that many scientists believe may be the very cradle of life on our own planet. A Martian ocean would have had all of this. It would have had thermal and chemical gradients, a complex soup of dissolved minerals and protection from the harsh radiation bathing the surface. It provides a robust planetary-scale engine for prebiotic chemistry, a crucible where the building blocks of life could have formed concentrated, and perhaps, just perhaps, made that momentous leap from inanimate matter to living organism. The question is no longer, was Mars habitable? The evidence now screams that it was perhaps on a scale as profound as early Earth. The new, more thrilling question is, did life actually arise? And if it did, where might its fossils or even its living descendants be hiding? The ghost of that ancient ocean guides our search. We must look to the sediments of the old sea floor, now buried under layers of dust in the northern plains. We must drill into the clays of the ancient river deltas like Jezero, where the organic signatures of microscopic life could be perfectly preserved. We must search for the mineral veins left by ancient hydrothermal systems, the places where superheated mineral-rich water once coursed through the planet's crust. We are no longer searching for a needle in a haystack. We are searching for a needle in a place that we know was once filled with needles. Life, if it ever began on Mars, may have been driven underground as the ocean vanished and the atmosphere thinned. It might still cling to existence in subsurface aquifers, warmed by the planet's internal heat, a shadow biosphere completely isolated from the hostile surface. The discovery of the ocean transforms the search for Martian life from a hopeful gamble into a focused, systematic investigation of a world we can now rightly call our sister. And the implications of this watery past ripple out far beyond Mars across the interstellar void. For eons we have stared at the countless stars in our galaxy, wondering how many might be circled by planets like our own. The James Webb Space Telescope is now beginning to sniff the atmospheres of these distant exoplanets, searching for the telltale signs of habitability. Mars provides us with a crucial, sobering lesson, a Rosetta Stone for planetary evolution. It is our closest and most accessible example of a paradise lost. It shows us that possessing the ingredients for life is not enough. A planet must also keep them. Mars teaches us that a world's habitability is a fragile, fleeting state of being. It had a thick atmosphere, a magnetic field, and abundant liquid water. But it was smaller than Earth. Its internal dynamo cooled and sputtered out its protective magnetic shield, vanished, and the relentless solar wind began its work stripping the atmosphere away, molecule by molecule. The pressure dropped, the planet grew cold, and its great ocean either froze into a vast subterranean cryosphere or was blasted away into space. When we look out at a rocky exoplanet in the habitable zone of its star, we can no longer simply assume it is an Earth-like haven. We must now ask, is it an Earth or is it a Mars? Is it in the vibrant spring of its youth, or is it in the deep frozen winter of its life, its watery past just a memory written in its geology? The story of the Martian ocean is a cosmic cautionary tale, a vivid demonstration of the thin, precarious line that separates a living world from a dead one. It gives us a new and vital data point in our quest to understand our own place in the cosmos, refining our search and reminding us of the incredible confluence of factors, size, geology, magnetism and sheer luck that allowed Earth to remain a blue marble while its neighbour became a red fossil. Mars is no longer just a target for exploration. It is a fundamental part of the comparative planetology that will one day allow us to look at a dot of light trillions of miles away and say with confidence whether we are looking at a home. This profound new understanding of Mars's past inevitably shapes our vision for humanity's future. For those who dream of walking on the red planet, of building the first human settlements beyond Earth, the ancient ocean is not just a historical curiosity, it is the single most important resource for the future. That water didn't just disappear. An immense quantity of it is still there, locked away as vast sheets of subsurface ice and frost, particularly in the northern plains where the ocean once stood. We now know where to look. We are not planning to go to a dry, barren world. We are planning to go to a world with in situ water reserves of continental scale. And for a fledgling human colony, water is everything. It is for drinking, for growing food, for shielding against radiation. But it is also a source of breathable air because you can split water molecules into oxygen and hydrogen. And that hydrogen, combined with the carbon in the thin Martian atmosphere, is the key ingredient for manufacturing methane rocket fuel. The ghost of the ancient ocean literally paves our way to the stars. Future Martians will be water prospectors drilling into the soil to tap the frozen remnants of that primeval sea. Their habitats, their farms, their fuel depots will all rise from the dust of the old ocean floor. In a strange and beautiful turn of cosmic fate, the very same element that may have given rise to Martian life billions of years ago will be the element that sustains a new form of life ours on its surface. Our journey to Mars will not be a conquest. It will be a return of complex life to a world that was once brimming with potential, a rekindling of a planetary fire that went out long ago. We will be explorers standing on the shores of a new kind of sea, an ocean of possibility, its waters drawn from the ice of a distant past. From here on the precipice of this new era of discovery, we look back at that faint red light in our night sky, and it is forever changed. It is no longer just a symbol of the alien and the remote. It is a place of memory, of loss, and of immense sleeping potential. Mars is a mirror reflecting both the incredible dynamism of planetary evolution and the tenacity of our own quest for knowledge. It is a world that challenges us, that forces us to be better scientists, better engineers, better explorers. It reminds us that worlds are not static objects but have lives of their own, that they are born, they flourish, and sometimes they fade. The story of its great northern ocean, a story we are only just beginning to read in full, is one of the grandest tales in our solar system. It is a story of a sister world that was almost but not quite like ours, and in that gap between almost and is, lies the adventure of a lifetime, an invitation across the dark to come and explore, to learn its secrets, and perhaps one day to call its silent shores home. The water is gone, but the wonder remains deeper and more vast than the ocean itself.